Hello, I'm Pahan and I'll be explaining the vulnerabilities I identified and fixed in the Eatsy food delivery application under the topics broken authentication and insecure design, potential injection vulnerabilities, and finally our Google OAuth integration. In our authentication system, I found several issues. First, JWT tokens were stored in local storage, making them vulnerable to cross-site scripting attacks. And second, there was no refresh mechanism. Tokens lasted 3 hours and could not be revoked once issued. And third, we lacked input validation in login forms, creating a risk of credential stuffing. Finally, logout was insecure since tokens were only detected client-side but remained valid on the server. And this is the authentication flow of the unsecured version. These issues were found through SAP scans, manual testing with browser developer tools, and static code review of the authentication controllers. To fix them, I replaced local storage with HTTP-only secure cookies, introduced a refresh token mechanism with short-lived access tokens, and added server-side invalidation during logout. Additionally, I enforced input validation using the validator library and added rate limiting with express rate limit to block brute force attempts. In the backend controllers, I discovered potential NoSQL injection vulnerability because unsanitized user input from rec body and rec params was passed directly into MongoDB queries like find1 and find_by_id. This could allow attackers to inject malicious operators to bypass authentication, access unauthorized data, or even crash the database with expensive queries. To fix this, I used Express Validator for strict input validation and Mongo Sanitize middleware to automatically clean malicious operators from requests. I also added model-level validation in Mongoose to reject unsafe data early. These steps prevent malicious payloads from being executed. Finally, to strengthen security and improve user experience, I integrated Google OAuth 2.0 with OpenID Connect using Passport.js. This allows users to log in with their Google accounts, eliminating weak password risks for those users. The OAuth flow uses the authorization code grant type, retrieves a secure token from Google, and then issues a short-lived JWT compatible with our microservices. This enhances both security and scalability by delegating authentication to Google. Here's a small demonstration of implemented Google OAuth authentication system.
Everyone, I'll be talking about the vulnerabilities I've detected and fixed in Eatsy. The first is the role-based access control. When I try to manually enter the URL, I'll be able to access information that only an admin should be able to. And in the customer side, when I try the restaurant URL, I'm able to access restaurant information. So to handle that, I've done access control in both the client side and also the controller side. So I've considered a verify user role function, which checks whether the expected role is that of the actual role. So now if I try to enter the URL, I get please sign in. And in this side, when I try to go to restaurant, I get access denied. And then the other thing is in the controller function. So if I go to this specific controller function, I've called something called authorized restaurant, where here also it checks whether the actual role of the user is equal to that of the expected role. And here, if you try to test it, first I'll give this no data, it says unauthorized. Then I'll try to give the token of that of a customer, and it says forbidden access denied. I'll give the token of that of a restaurant, then it gets the data. Then the other change I've done is about the DOS attacks. I've included both a rate limiter, which is to limit the amount of requests per each IP address, I've called that, and the other thing is the connection timeout. So the connection timeout is being done to handle Swarovski's DOS attack, which tries to keep as many connections as it can and amp up the hardware resources. So those are the changes I've done. So I've come up with some scripts to test that. I will not be running this again because of the time limit. But when it goes and exceeds more than 100 requests as per the rate limiter, it says too many requests, please try again later. And when it comes to the solve process, it initially opens up 50 requests, and over time it delays the amount of delays the time that each request takes, and over time, because of that, the sockets start closing up. So that is what happens in this Python test. So that's it for my vulnerability testing and fixing. Thank you.
Addressed security vulnerabilities in the Eatsy food ordering web application by fixing two key issues: security misconfiguration and security logging and monitoring failures. Security misconfiguration. The first problem was with CORS and the database setup. For CORS, the API gateway was too permissive. It allowed any origin to access sensitive endpoints, including order creation and payments. This opened the door to risks like cross-site request forgery and data theft. I fixed this by configuring the express.js CORS middleware to only allow trusted origins defined in environmental variables, for example, localhost during development and future-hosted domains when deployed. I also restricted allowed HTTP methods to just what the app needs, which reduced the attack surface. The second issue was public database exposure. A MongoDB Atlas cluster was set to accept connections from any IP address. This meant anyone could potentially access user profiles and order data. To secure it, I updated the IP access list so only trusted static IPs are allowed, with automatic expiry for temporary access. Security logging and monitoring failures. The second big issue was poor logging. Eatsy mostly used console.log, which wasn't reliable, and the way strings were logged even left us open to log injection attacks. Without strong logs, things like unauthorized access or fraud could go unnoticed. I solved this by integrating the Winston logging library. Instead of plain text logs, the system now records structured JSON logs with timestamps, severity levels, and sanitized metadata like user IDs. By avoiding strict concatenation, it blocks injection risk and ensures logs are trustworthy. These fixes strengthen Eatsy's security by protecting sensitive data, reducing attack surfaces, and ensuring incidents can be detected and addressed quickly. Overall, they boost user trust and safeguard Eatsy's reputation in the food delivery market.
In this project, I focus on fixing two important security vulnerabilities: information disclosure and server-side request forgery. First, for information disclosure, the issue was that our APIs and frontend were showing detailed error like error.message and stack trace. This could reveal sensitive information such as database details or file path to attackers. To fix this, I removed error.messages from API responses and close messages. Now users only see safe, generic messages like internal server errors. At the same time, I added proper login on the server side, so developers still have full error details for debugging, but nothing sensitive is leaked to client. Second, for SSRF, the problem was that some service made out-of-bound HTTP request without validating the URLs. This could allow attackers to trick the system into calling private or internal endpoints. To solve this, I introduced a safe Axios wrappers and our URL validators. These check that only safe URLs are used and block requests to private IP range or non-HTTPS schemas. I then replace all direct Axios call in the code with these secure wrappers. With these changes, the system no longer leaks sensitive error details and it protects against the SSRF attack. Users see safe error messages, developers get proper logs, and out-of-bound requests are validated for security.